Welcome back to the third lecture of CS229. So in the first two lectures, we've been mostly going over the course prerequisites, linear algebra, probability. So on Wednesday's lecture, just to recap, we went over the concept of determinant, its geometrical interpretation, and we went through two different kinds of decomposition of a matrix, the eigenvalue decomposition and the singular value decomposition. After that, we quickly went through some matrix calculus, the different ways in which linear algebra plays a role in calculus when we are dealing with multivariate functions. And after that, we switched gears into probability to review some basics of probability theory. Today, we will finish up the review of probability theory and maybe in a few, just spend a couple of minutes on some basics of statistics, of why statistics plays a role in machine learning. And after that, we will jump right into our first learning algorithm, linear regression. That's the plan for today. Any questions about what we've covered so far before we get started? Okay, so we were reviewing probability and maybe let me just go back a few slides to just touch upon a few important concepts, right? So we covered what's a sample space. Samples are basically the collection of outcomes of random experiments, and events are subsets of the sample space. We assign probabilities to events, not to random outcomes, but to sets of outcomes, and those are the axioms of probability. We went over what is the meaning of independence with respect to events. An event is independent of the other if the probability of their intersection is the product of their individual probabilities. And then we discuss this concept of a random variable. A random variable is something that maps the space of outcomes, which could be anything. It could be a string of heads and tails. It could be the color of a die. It could be anything whatsoever. And we map it onto the real line. And that's when we can start doing mathematics with randomness. The concept of a random variable maps outcomes, which could be in any sample space, onto the real line, right? For example, we could have a random variable that counts the number of heads in a given event, and to map that event outcome. Let me say that again. So here we have an example of a random variable which takes as input the outcome. The outcome in this case is a string of 10 heads or tail coin flips, and that is just a string of heads or tail symbols. It's not a number. And a random variable, an example of a random variable in this case, is a random variable that just counts the number of heads in that sequence of 10 coin flips and maps it to a real number, right? And by values of x, we means the set of all possible real values that the random variable can possibly map any of the outcomes into. Right? And then we spoke about the cumulative distribution function. So previously we saw that a probability measure is defined on events, but once we map it to the real line, once we define a random variable, the probability measure kind of induces some kind of a probability measure on the real line, right? And that can be captured by something called as the cumulative distribution function. It is basically the measure or the probability assigned to the set of all outcomes which get mapped to a value less than or equal to the desired threshold, right? So this is how a CDF would look for a continuous random variable. So the height of this function is measuring the amount of probability assigned to the set of all events, the set of all outcomes that mapped less than or equal to the desired threshold. So that's what we have here. So it is the P over here is now measuring an event, a set of outcomes, and the set of outcomes is defined as the pre-image of the random variable, right? The random variable maps outcomes to the real line, and if we look at the pre-image of that function, that is the set of all inputs that get mapped to a value less than or equal to the desired threshold, that will give you a probability, and that's going to be a value between 0 and 1, and which is why the values of the CDF lie between 0 and 1. Right? And we spoke about discrete versus continuous variables. Discrete variables have a probability mass function, and continuous variables have a probability density function. Right? A CDF, or a cumulative distribution function, exists for all random variables. That is the CDF that we saw over here. A CDF exists for all random variables, whether it's discrete or continuous, but the density function exists only for continuous distributions, which is basically the derivative of the CDF. It's important to note that the density of the value returned by the density function is not the probability. What I mean by that is, if suppose this is x and we have some density function, and suppose this is 0.3, right, and this has some height, right. It's important to note that the probability of x equals 0.3 is not equal to this height, right. The probability for any continuous random variable, the probability that the random variable takes a specific value is always 0. That may sound a little counterintuitive if you're hearing this for the first time, but let me say that again. If we have a discrete probability, discrete random variable with a probability mass function, like 1, 2, 3, then the probability that the random variable takes on the value 3 is given by the height of the probability mass function. But the probability density function is something that's fundamentally different, in the sense the height of the density measured at that point is not the probability that the random variable takes on the value, for example, 0.3, right? Probabilities in case of continuous random variables are only defined on intervals or sets of intervals. So the area under the probability density function for a given range of your input, the area under the probability density function is the probability that the random variable takes a value in this range, right? But the probability that a continuous random variable takes any specific value is always 0, right? So that's yes, question. Mm-hmm.
So we can't quantify the value of the output, right? We don't know, it can vary anywhere. So how can we say it's 0? It can't be determined, because it's continuous. It can be, it doesn't have a certain output value, right? So how can we say the probability is 0?
Well, so the question is, if I understand you correctly, let me rephrase it and then you can tell me if I understood your question correctly, is we don't know where what value the continuous random variable is going to take, so how can you define the probability to be 0? Well, so this is, you can think of probability as so there are two kind of interpretations to probabilities. One is looking historically, what's been like the distribution of your true random variable taking on in the past, and then based on that you can probably construct some kind of a density or estimate some kind of a density. What it actually means is, just because if you take a continuous random variable, the number of possible values it can take is uncountably infinite, and that makes it impossible, or a continuous random variable does not have point masses, in the sense any given value in this, among this uncountably infinite number of possible values, any given value of these has zero probability of occurrence. But if you take a range, you get a probability for the value falling in that range. Right? Okay, so that's discrete versus continuous probability, and then we started talking about this very important concept called expectation. Right? Expectation is a concept that's only associated with a random variable. Right? So we spoke about outcomes, and we spoke about events. Right? And we defined a probability measure on events. So if we limit ourselves to just these concepts, then the concept of expectation does not come into picture. Yes, question? Lights. Is it okay? Okay. Can you see the slides as well? Is it too bright for the slides? Right. Okay. Okay. So if we are only limiting ourselves to the concepts of outcomes and events, then there is no such thing as an expectation. But once we define a random variable, right? A random variable, as we saw last time, was it. I'm going to draw the outcome space as, or the sample space with a squiggly line, just because it's not like a linearly ordered line. And then we define a random variable. So assume this is some random variable x that maps outcomes to the real line. Right? You could have another random variable which maps the same sample space to the real line in a different way. Let's call this y of omega. Now, only after we define this concept called a random variable, the concept of expectation comes into picture. So expectation is what is the, well, an informal way to think about expectation is what value does this random variable take on average, right? So we have a function, right, that maps outcomes to the real line, and generally we kind of flip this axis over, and we start with the vertical line flipped over, and we ask ourselves, suppose there is a function g defined on top of this random variable. So let this be some function g of x, and this is x, and the values over here are those values are coming from coming from outcomes that got mapped onto the real line. And then the expectation is now asking what is the average value that g will return, right? And the average value that g returns is going to depend on what values we are feeding into x, right? And what expectation informally is, if we feed values into g according to the distribution that is induced by x, right? So events happen, you sample events, right? Map it to x through the random variable, feed that value of x into g, and you get some value, right? So suppose this outcome happened, map it to x, right? X maps it to g, and this is the value of g, right? And similarly, you repeat this experiment over and over, right? Different outcomes map you to different values of x, and different values of x map you to different values of g of x, and you're measuring the various values of g, and you're trying to ask the question, what's the average value of g in general, right? And you can ask the question of average value only because now you have things on the real line, right? On the sample space, there's no such thing as an average. There's no such thing as an average sample, because you have a die with 6 colors. What's the average color? It's not meaningful. Once you map them to numbers, you can ask what's the average value, right? And for a discrete random variable, the expectation is defined like this, right? Sum over all the possible values x can take, and for each of those values, multiply g of x, that is the value g of x returns, times the probability x takes that value, right? And this is just a weighted sum of the different values of g of x according to the probability with which x can occur, right? Very intuitive definition of expectation. And similarly, for continuous random variables, it's defined like this. In place of the summation, we have an integral, right? Now you're integrating over all possible values of x, right? And for each value of x, we measure the density, right? Not the probability, but the density. And because we are now using densities, we now have an integral instead of a sum. Right? Is question?
So g of x here is like a distribution of our random variable, right?
X. So what the question is, what's g of x? So x is a random variable, and g of x is some function of x. It's just some function of x, right? It's g is defined here. G is some function that takes a real value as input and outputs a real value, right? And you can, if g is just a function, in this case, the input of x, input to g is going to be the random variable, which means it can take on different values according to the outcome of some random experiment. Right? So that's the expectation of g of x, and we saw an important concept in the last lecture, that you can approximate g of x by taking random samples of x and calculating the average of g of x for that sample, right? And that's called the Monte Carlo estimate of the expectation. And as the number of samples tends to infinity, right, as you estimate the expectation with more and more number of samples, the Monte Carlo estimate converges to the true expectation, right? And that's basically the law of large numbers. Right? Any questions about that? Right. So that was still that's what we covered on Wednesday, and today we're going to continue further. Now we're going to talk about variance. So what's the variance of x? Variance of x is defined as, was there a question? Right. So the variance of x is defined as the expectation of x minus expectation of x squared. Now what's happening here? It basically means, suppose x has some distribution. For example, let's suppose this is the probability density of x. Right? The expectation is also the point that's kind of the point that's you can think of it as kind of the if you imagine this probability density function to have some kind of a shape, then the expectation is that point on x, which is basically like the center of gravity. Like, right? If you take an actual physical thing of this shape and you try to balance it on the expectation, then your that shape will kind of stay balanced, right? It's like the center of gravity, right? That's the intuition for expectation. The variance is kind of trying to measure how spread apart is this random variable around its mean. So this is going to be the expectation. The variance is trying to measure how spread apart is this distribution in general. Right? There is also another concept called the median of the distribution. So the median of the distribution is, supposing this is the median. The median of the distribution is the point that divides the mass into equal masses on either side, right? And for symmetric distribution, the median and the expectation are the same, right? However, there could be distributions which are for example, you have a distribution like this, right? In this case, the median could be somewhere over here, but the expectation could be so this could be the median and this could be the expectation, because the point where you balance a mass is not necessarily the point where you have equal masses on both sides, because I think that's called the moment of inertia or something like that, where if you have mass that's kind of spread all the way on the other side, then that has more effect. So if you want to balance things, that's the point where that's the mean or the expectation, and median is the thing that divides it into equal masses on both sides. Right? And the variance is trying to measure how spread apart is this. If you could have a distribution that has a given expectation and a small variance, or you could have a distribution that has a given expectation and a large variance. Right? These are two different expressions for the variance of x, and they're both equivalent. That's showing this is pretty simple. It's in the notes. And here are some examples of various distributions and their parameters. Right? Parameters. Now, this is the first time we're talking about parameters. What's a parameter? Right? So when we're talking about distributions, there are kind of two concepts. One is the space over which the distribution is being defined. Supposing it's a random variable, it is the real line on which the distribution is being defined. And then you have a parameter. A parameter is basically a number that tries to summarize the shape of the distribution. Right? For example, if you have a Gaussian random variable, which is also called the normal distribution or the bell curve, it has two parameters. So one is so this is the real line, and this is the Gaussian PDF, and mu is the mean of the Gaussian distribution, and sigma is like it's called a standard deviation. Right? So a Gaussian distribution is summarized by mu and the variance sigma square, where sigma is the standard deviation. Similarly, there are many different distributions, and each of them have parameters. Some distributions have just one parameter, some have two, some have three. But most of the distributions we're going to be interested in this course are going to have one or two parameters. Right? You can have you can look at two random variables jointly, right? And for that, what that means is, supposing you have a variable x and a variable y, together they have a joint CDF, which means the probability that the variable x is less than the x threshold, and the probability that y is less than the y threshold, right? So you think of the comma over here as the logical AND, right? Similarly, you have a bivariate probability mass function, which is the probability that x, in this case x and y are discrete. In the continuous, they were here they were continuous. So this is the probability that x takes the value small x, and the random variable y takes the value small y. Given the joint PDF of two random variables, you can construct their marginals. Right? So if you have two random variables, let's call it x and y, the distribution that captures the most information of these two is the joint distribution of the two. And that will have, assuming they are continuous, you write it as p of x comma y. Right? That's the joint distribution of the two. Similarly, you can have the marginal distributions of the two random variables, and the marginal distributions is going to be written as p of x or p of y. And the way you get these is to what's called as marginalizing out or summing out or integrating out the other variables. So sum of all the y p of x comma y, and you get this. Or similarly, if it's a continuous random variable, then you integrate out p of x comma y dy, right? And this is just the other way. So here you sum out x if it is discrete. So this is discrete, and this is continuous. Right? And here it will be summing over. Right? Now the way to think about the joint PDF is that the joint PDF or the joint PMF has to satisfy the property that right. So if you integrate out both the variables, the joint PDF has to integrate to 1, right? And if you integrate out only one variable, then you get a distribution with respect to the other variable, right? And that's called the marginal distribution. Right? So given these concepts of the joint and the marginal, we can define the Bayes theorem. The Bayes theorem is probably one of the most important theorems in probability theory. It's going to show up all over the place, especially in this course and even beyond. And the Bayes theorem basically gives you the relation between the conditional distribution, the joint distribution, and the marginal distribution. Right? So the Bayes theorem looks like this. So p of x comma y, you can write this as p of x times p of y given x. Right? So this is the joint, this is the marginal, and this is the conditional probability. Right? So the way you want to remember this is the joint is the product of the marginal and the conditional. Right? But you can also write this as p of y times p of x given y. Right? And the way you decompose the joint into these two parts is called the chain rule. Right? So there's a chain rule in calculus, there's the chain rule of probability theory. Right? So the chain rule tells you that you can always, for any pair of random variables, you can decompose the joint into the marginal times the conditional. Right? And a trivial consequence of this chain rule is the Bayes theorem. So the Bayes theorem basically equates these two. So you write p of x times p of y given x equals p of y times p of x given y. Right? And assuming p of x is never 0, you can divide both sides by p of x, and that gives you p of y given x equals p of y times p of x given y over p of x. Right? So this is Bayes theorem. Right? It's a very simple consequence of the chain rule. You apply the chain rule in two different ways, equate the two different ways, and divide over by one of the marginals, and you get the Bayes rule. Yeah, so here we are writing this in terms of f, but you can use f or p, doesn't matter. Right? And another way in which the Bayes theorem is also commonly written is retain the numerator as it is, p of y times p of x given y, and the denominator is, instead of writing it as p of x, you're going to write it as, assuming it's a discrete, sum over y prime, p of y prime times p of x given y prime. These two are the same. Why are they the same? Because p of y prime times p of x given y prime is the joint. Right? It's the joint, and you're marginalizing out y prime from this, which gives you p of x. Right? maybe, just to add, this is basically equal to summing over y prime of p of x comma y prime. Right? We're going to use this form of the Bayes theorem also in this course. Right? Any questions? So some of you sitting over here, you may not be able to see this, read this, because this kind of comes in the way. So maybe you can move over next time, or you can move over even now if you want to. Right, example of Bayes rule. Let's skip over this. Independence. So the independence of two random variables is very similar to the independence of two events. They are distinct concepts. Independence. We spoke about independence of random events a few slides ago. Here we are talking about independence of two random variables. And the independence of two random variables is defined like this, that the joint probability is equal to the product of the marginal probabilities, right? Or the joint density is equal to the product of the marginal densities. That also, that's basically telling, if it is independent, right? You're saying p of this is equal to p of x times p of y. So if two random variables are independent, then p of y must be equal to p of y given x. Right? We saw something very similar for random for independence of random events. It's very very similar. So p of y given x of two variables will be equal to p of y. Yes, question. So the question is, if two random variables are independent, can we say that the events that they are defined over are also independent? It must be the case, right? Yeah. Yes, question. Yes, question. Go back a slide. This is defined when f of x is not equal to 0. So the when the probability, so assuming we are talking about discrete, in the discrete case, the conditional of y given x itself is not defined if the probability of x is 0. Right? Assuming that the conditional is defined, the Bayes theorem tells you that you can represent it like this. Does that make sense? So the conditional probability itself is defined only when conditional of y of x is defined only when x has a non-zero probability.
Can you explain the interpretation for that function f of y given x? What does it actually mean?
So over here, this is the conditional distribution of y given x takes on some, a given value. Right? Right. Next, we're going to talk about this, independence. So we're going to, independent random variables are super important because it lets you decompose the joint probability into just product of the marginals, and this independence makes is what makes a lot of machine learning theory kind of easy to work with. We are going to be making assumptions about your training examples, which you think of them as random variables being independent of each other. So the concept of independence is very important. Right, let's skip over this. Right, this is the expectation of two random variables. You can go over these in your slides. Just like the concept of of variance, there is the concept of covariance when we are talking about two random variables. Right? And the covariance of random variables are defined like this. So, so the variance of x was defined as expectation of x square minus expectation of x square. We saw this on a few slides ago. Similarly, the covariance of x comma y is defined as expectation of x times y minus expectation of x into expectation of y, which basically tells you that the covariance of x with x is just the variance of x. Right? All right, the multivariate Gaussian. So this is one of the most commonly used distributions defined over a collection of random variables, right? And this is something that's going to show up a whole lot in this course, and hopefully towards the end of the course, if you're woken up in the middle of your sleep and asked you what's the probability density of a multivariate Gaussian, you'll be able to say this, instinctively, right? This looks a little scary at first, but let's kind of dissect it a little bit. So x is in some n-dimensional space, and the probability, the density of x given two parameters mu and sigma is defined as 1 over 2 pi to the n by 2 times the determinant of sigma to the power half times the exponent of minus half x minus mu transpose sigma inverse x minus mu. Wow. So, first of all, let's see what's happening here and add some color to it. So, x is the space over which we are defining the probability density. So, we see that x appears only here inside the exponent, right? And you have two parameters, mu and sigma. The sigma is called the covariance matrix, and mu is the mean. And the covariance matrix shows up over here. So let's inverse, and then we have the mean, and the mean maybe I'll use black for this. Oh, that's not working. Mean. All right. So this is the joint the joint distribution of a multivariate Gaussian, and we right away recognize a few things that we have seen in our linear algebra course before, right? So first of all, sigma is a matrix, right? It's called a covariance matrix. It turns out to be a positive semi-definite matrix. Any covariance matrix for any joint distribution, no matter what the distribution is always going to be positive semi-definite, right? So this and this is a positive semi-definite matrix, and it is going to be full rank, which means the inverse will exist, right? And we recognize a few more things. So this is the determinant of the matrix. Right? That's the notation for the determinant, and it's like the square root of the determinant. And we also see this form of it over here. Does anybody recognize this form? This is the quadratic form. So x minus mu is some vector, right? And what we are doing is x minus mu transpose some matrix times x minus mu, right? So this is the quadratic form that we also spent some time on, right? So all the review that we did with linear algebra is going to apply on this shortly, right? And this term over here is just some constant. It has no mean, no data, no covariance. This is just some constant. And the purpose of this 1 over 2 pi to the n by 2, the purpose of its existence is to only make this, the integral of this with respect to x, be equal to 1. So this is just some normalizing constant, right? Yes, question? Exactly. So the question is, if this is a multivariate distribution, what does the integral with respect to x mean? It means exactly what you said. You're integrating out all x1 through xn. Right? You hear me? Okay. Yeah. Okay. Sorry. The integral would look something like this. You would have p of x mu sigma square times dx1 dx2. Right? It would be a double integral or a triple integral or right. So this is the multivariate Gaussian density, and we're going to be working a whole lot with this. So you'll get familiar with this if you're not already. And here are some intuitions about what the mean and covariance matrix of a multivariate Gaussian looks like. So what we have in the left are examples of particular instances of mu and sigma. The figure on the center is a plot of the probability density function. Here it's a two-dimensional Gaussian, and the figure on the rightmost column is what's also called a contour plot or a heat map, where a lighter color, a color of orange, means that region has a higher value, and blue means it has a low value. So imagine looking at the plot in the middle directly from the top and using different colors to represent different heights. Right? That's the plot on the right. Right. So let's just get a feel for what the different parameters mean in terms of the probability density. So a mu equal to 0 means the center of the distribution, or the distribution is going to be centered around 0, 0. Right? We see this to be the 0, 0 over here, and the peak of the distribution is over 0, 0 in this case. And the covariance matrix, the diagonals of the covariance matrix are the variances of the marginals of x1 and x2. Right? So what this roughly means is that x, the variable x1, so if you just look at x1 over here, it's going to have like a standard deviation of 1. That looks roughly correct. If you imagine this to be the x direction, it has like a standard deviation of 1, and x2 also has a standard deviation of 1. And the cross entries in the covariance matrix are the actual covariances between those two random variables. A covariance of 0 here roughly means that there is no strong relation between x1 and x2, which makes it takes a spherical shape. Moving on, so here's another example where the covariance matrix has smaller diagonal elements, which means the distribution is still centered around 0, but it is more concentrated. It has a smaller variance, right? Which means it is more peaked. Okay, it is more peaked compared to this distribution. And in terms of the contour plot, the circles just appear to be smaller. Right? And similarly, if you increase the variance of your distribution, the covariances are still 0, which means it is still spherically shaped. Right? Now it looks more flattened. Right? Your probability density looks more flattened, and the concentric circles are also more expanded. Right? Let's look at a few more examples. Now, over here, this is still the first picture. Now let us scale the x1 to have variance 0.6 and x2 to have variance 1. So x1 is now more compressed, but x2 still maintains the same variance. So you see from the contour plot over here that it is more vertically aligned. Probably the slides, the shape, the projection of the slides make it look a little different, but that's the it seems on the picture over there, this looks like a circle, but it's supposed to be compressed vertically, and it's supposed to be longer. Now, instead of shrinking x1, if we expand x1, right, now you see that it's stretched across more widely, right? But still, there's no correlation between x1 and x2, so you don't see any particular correlation over there. Now let's add some correlation, right? Now x1 and in this case, x1 and x2 still have a variance of 1 and 1, but now we've added a correlation of 0.5, which means as you increase x1, x2 also tends to increase. That's the general idea, that x1 and x2 tend to co-occur more as you increase the values of x. If you increase the covariance further, the relation becomes even tighter, even stronger. Right? The marginals in this case are still 1 and 1, which means from if you were to integrate out x1, you would get a probability density of a unit of mean 0 variance 1 on x2, and similarly if you were to integrate out x2, you would still get a normal curve on the x1 axis. Right? So that this intuition for how a multivariate Gaussian would look. With 2 dimension, it's easy to visualize and get some intuitions. Right? So if this is the next slide, and if the correlation is negative, now what this means is larger values of x1 tend to co-occur with smaller values of x2. Right? So for example, over here, for x1 equal to for x1 to have a particular color, x2 has to be negative. That's what it means. So you see a reverse relation between x1 going up and x2 going down. And if you again make it negative and make it a bigger number, you see a stronger correlation between x1 and x2, but in the reverse direction. Similarly, for a given covariance matrix, you can move your use a different mu, which means the covariance matrix is deciding the shape and orientation of this function, and mu tells you where to place it, where to center it. Right? So this is basically the same bell-shaped, but placed at x1 equal to 0 and x2 equals 0.5. So here you see it's just in terms of x2, it's moved up a little bit. Right? And this is another example where x1 is 1.5. The center of the distribution is at x1 equals 1.5 and x2 equals minus 0.5. That's where the center is, and the covariance matrix decides the shape and orientation. Right? Any questions? Yes, question.
So the correlation in both the values was seen to have, it was 2 dimensions. If we increase the dimension, is it possible that the correlation of one to the other
So if you the question is this is with respect to two variables, and what if you have more variables? Is that the question? Yeah, so if you have a three-dimensional Gaussian, then you would have a 3 by 3 covariance matrix, and each of the pairwise correlations will be the values in the corresponding cell. Right? Okay, so conditional probability, we went over this already. So here's a useful identity, which is the conditional expectation. Right? So the conditional expectation is another important concept in probability, and the conditional expectation is defined like this. And the conditional expectation is actually somewhat subtle, right? So conditional expectation is so the conditional expectation of E of x given y. So you think of the conditional expectation in this form, where x and y are random variables, to be a random variable. Right? The expectation of x is a constant. Right? But the conditional variable of expectation, the conditional expectation of x given y is another random variable. Right? X is random, y is random. Expectation of x is just a constant; it is not random. Right? The conditional expectation of x given y is a random variable. Right? It's a random variable defined over the space of y. However, conditional expectation of x given y equals small y, this is a function of small y. Right? The conditional expectation of x given y, where you're just placing the random variable over here, is another random variable. Right? It doesn't look like it, but x given y, conditional expectation of x given y is another random variable. But the conditional expectation of x given y equals some specific y is a function of that specific y. Yes, question? These two are not the same in the sense this is still a random variable. This whole thing is a random variable, and this whole thing is a function of small y. This is a subtle concept, and you may want to go back to your probability book to kind of go through this again. But this can be relevant in some of your homeworks. So that you want to have a good clear understanding that or view these as distinct things. Conditional expectation of x given y, where y is still a random variable, is another random variable. It is basically you're saying you're feeding a random variable y as input, and this becomes a function of y, and therefore it's still a random variable. You can think of it that way. Yes, question? Exactly. So the question is, if this is a random variable, then can we apply all the rules that we've seen so far on this? Exactly, you can, but you cannot on this one. Yes, question. So over here, the random variable is defined over the space of y only. Yes, question. Random variables are functions already. This is a function of y, of over small y, but this is a random variable in the sense this is a function over your sample space. Think of it that way. This is just over the sample space of y alone. So maybe the next slide might make it a little more clear. So maybe hold your question until the end of the next slide. And was there one more question? Yes, question. Mm-hmm.
If you set y and you have a distribution over x, is for a given value of y type of constant. So if you make y equals 3, then expectation of x given y equals 3 is a constant, right?
Yeah, so in the case of Gaussian, you can think of it like this, right? So assume this is the contour plot of Gaussians where it is centered on some, let's call this say +1 and +2, and the expectation, and let's call this x and let's call this y. So the expectation of x given y equals say some small value y, and assume the small value y is this, right? What it basically tells is if you kind of limit yourself to this slice of the Gaussian, and that's going to be that's going to have some kind of a bell shape, and what's the expectation over there? Yes, question? So this is a function of small y. Expectation of, that's a typo, that should be small y, sorry. Yeah, this over here should be small y, thank you. Yeah, so now we have something called the law of total expectation, right? So the law of total expectation tells us that expectation of x can be written as the expectation of x given y, right? Now this holds true for any x and any y, right? Y could be completely independent of x, it could be dependent on x, but the expectation of x can always be decomposed into this nested form where you condition on y, you get a new random variable, right? And you take the expectation of this random variable and you get back the expectation of x. This is called the law of total expectation. While this holds true for any y in general, you have the choice of choosing the y, and you want to choose a y that makes your problem easier to solve by breaking it down this way, right? And the choice of what y you want to choose is more of an art, and you got to when you're asked to calculate the expectation of x, and it's pretty complex. You want to use some creativity in choosing a y to defining this random variable, and then take the expectation of that, and by breaking it down into like sub problems, you can solve some complex problems. So the expectation of x given y, where y is left unspecified, is a random variable, and that's what shows up here in the law of total expectation. And when you take the expectation of that, you get back the expectation of x itself. Yes, question? This one? Yeah, you can think of it as a function of big Y. That's one way to think of it, or just think of this as a random variable. This is a random variable, like z. Think of this as z. Some random variable. Right, here's a proof to show this proving law of total expectation. I'm not going to go over this. You can go through this yourself. Pretty straightforward. There's nothing complex going on here. And there's one more version of Bayes' rule that's going to be helpful for you. Right, so So let's write the Bayes rule that we've already seen. P of A given B is equal to P of B given A times P of A over P of B. Right? So this is the Bayes rule that we saw already. Right? And the Bayes rule basically also allows you to have another variable that is conditioned throughout. Right? So you can think of this as the conditional Bayes rule, which means P of B comma C. Right? So you can have C conditioned in all the terms, and this is also Bayes rule, the expression that you see over here. Right? Similarly, you can also so this is the Bayes rule where we are kind of swapping A and B over here. Similarly, you could have also just as well kept B conditioned throughout and just swapped A and C. Right? And that's also you can think of that as Bayes rule. All right. Any questions? Okay. With this, okay. So here's a proof for this. You can go over this, but you can just remember it this way and you can apply it. This proof is just to convince yourself. We're not going to test you on these kind of proofs. With that, we finished the review of probability. Any questions? Now, I want to take a few moments to kind of give you a big picture overview of the role statistics plays in machine learning. Right? What we saw in the slides so far, right? We had parameters. Right? For example, mu, sigma of the Gaussian, right? And we had observations. We had parameters and we had observations. For example, in the multivariate Gaussian, you had x in some Rn. Right? So, probability basically is the field where you're trying to make statements about the observations given your parameters. Right? Probability. Right? So given parameters, you're trying to make statements about the data. What is the probability of this? What's going to be the marginal probability? What's the conditional probability? What's the joint probability? Things like that. So given parameters, we assume that the parameters are given or they're fixed, and you're making statements about observations or data. You can think of this as data. Right? And statistics is kind of doing like the opposite. Right? You're given data, you start with data, and you're trying to make statements about your parameters. Right? You make some assumptions in statistics about what the distribution is, given the data, and you take the data that's given to you. Right? You're not making statements about what the probability of some other data is, or anything like that. But given the data, you're trying to make statements about the parameters, right? And that's statistics. And you're trying to generally the statements that you make about the parameters in statistics are about things like, is this parameter value equal to 0, or is this parameter value much farther away from 0, right? And you're going to assign p-values for those observations. You're going to define confidence intervals where what you believe the range for those parameters are, right? So you start from data and make statements about the parameters in statistics, but in probability you're kind of going the other way. And these two are kind of like yin and yang. They're kind of coupled to each other, right? And there are many techniques to estimate parameters given your data, right? So things like method of moments, or maximum likelihood estimation. And it is this approach that's kind of relevant for us in this course and for most of machine learning. And using these techniques, you kind of feed in x as the input for these techniques, and it's going to output some parameters for you. Right? Now, where does machine learning come into picture? So with machine learning, what we are trying to do is you're given what's called as a training data. Right? Your training data is going to be some collection of x. You can think of them as XY pairs for supervised learning, and you're given a collection of them, right? And given your training data, you want to learn the parameters of your model. You're going to define some kind of a model for this data and learn the parameters. And using the learned parameters, so for machine learning, you feed training data, right? And you're going to learn your model. And using those models, you want to make predictions about future data. Right? So machine learning, we are actually, the goal that we are interested in is actually, given the training data, make predictions about future data. Right? But incidentally, we kind of take statistical approaches where we build a model and use the model to make predictions on future data. And that's where kind of statistics comes into picture, where you're given training data, we use tools from statistics like maximum likelihood estimation and other things to learn the model. Even though we are using the same tools of statistics, the goals are very different. In statistics, the goal is to make statements about the parameters itself. Right? In machine learning, we really don't care about the parameters at all. All we care is how good is this model in making predictions about future data. And that's how we measure the quality of machine learning methods. How good is it in making predictions about future data. Whereas in statistics, the game ends here. We measure how good the model is or how good our method is in terms of making proper statements about the parameters. Right? In machine learning, this is a black box for us. Right? It does estimate your parameters, but they are not of direct interest to us. We are only interested in the parameters because they help us make predictions about future data. Right? And this part of the cycle is also what is called as learning or training or fit a model with data, right? And in classical statistics, you also call this statistical inference. Right? You're inferring what the parameters are given the data. And once you have data, this is called prediction. Right? You are making predictions about future data, about unseen things, things that you haven't seen before, about data that you haven't encountered before. Right? And which brings us to maximum likelihood estimation. Right? In maximum likelihood estimation, I'm going to call it MLE. Now, MLE, let's start with a very simple example of MLE to kind of give you the flavor of. Let's start with Gaussian data. So here we are going to talk about a simple situation where we are given data x in RD, and you're given a collection of them. I'm going to write them as x1 through xn. In this notation, what I mean is each xi is the ith example. It does not mean x raised to the power of I or x raised to the power of n. Whenever I write a superscript with parentheses, it means it's the ith example. Right? And there are n such examples. Each example is, in Rd. So it's each xi is a d-dimensional vector, right? And we are given, let's assume we are given n such examples, right? Now, the probability, we already saw the probability density of the Gaussian, which is p of x given mu comma sigma is equal to 1 over 2 pi to the d by 2 sigma half exponent right. So this is the probability density, right? Now, we are now going to define something called as the likelihood function, right? So let's define the likelihood function of the parameters mu comma sigma given the data x. Okay. And for notation, let's call x as the collection of your n examples, and over here the semicolon means things to the right are kind of think of them as parameters or think of them as given values, and the function is being defined on the variables that are to the left of the semicolon. Right? In order to define the likelihood function, we are going to make yet another assumption. The assumption here is that each of these are sampled independently and identically distributed. Right? So this is also commonly called IID. And this is going to be a very common assumption in all machine learning methods, that the training data that you have are sampled in an IID fashion, which means x1 through xn are all independent of each other. They were sampled independently. Right? Now, we define the likelihood function as so this was for one example. Let's make this for all the examples. So the probability of x1 through xn mu comma sigma is going to be, we saw independence that p of x1 through xn. If x1 through xn are independent of each other, we can write this as the product of I equals 1 through n p of xi. Right? This means product. You're multiplying the terms over here. Right? Yes, question? All right, let me, I haven't finished this yet. So let me come back to this in a moment. Right? So the joint probability of independent pieces of data is the product of the individual marginals. Right? Now, if you want to define the probability density of your full data set, x1 through xn mu sigma, we're going to write this as the product of I equals 1 through n, 1 over 2 pi to the d by 2 half exponent minus half here x I minus mu transpose. Does it make sense? Because we are making, think of this as, this was for the case of one example, but if you are given, an entire training set, the probability density of the full training set, because of the IID assumption, we can break it down into the probabilities of individual examples and just multiply over them. Yes, question? Yeah, here X is a vector, right? X is a vector of D dimensions, yes.
In the above case, X is just a variable, right? It's a single variable.
So in this case, X is also a vector, right? So you have X minus mu transpose. This is still in a vector setting. Right? So this is for one example where the example is still vector valued, and this is n examples where each of the example is still d dimensional. Yes, question? So the semicolon is a way of saying things that come to the right, you're treating them as given. You don't think of them as variables; they're just some constants. Right? Now, so this is the probability density, and it is precisely this IID assumption that lets us break down a complex problem into smaller pieces. Right? It's representing this as one large Gaussian would just makes it a harder problem. We don't even know, what this distribution might look like if there is, if the interactions are pretty complex. So instead, when we make the IID assumption that your training data just came to you, each example was generated independently, we break it down into, smaller problems. Now, once we have this, this as the probability density, we're going to now define the likelihood function. So the likelihood function is, in the spirit of this, a probability density function takes x as your data, x as your data as the variable, and assumes your parameters to be given. But for going the other way, we're going to take your data to be given, and your parameters are the thing you want to make a statement over. So over here, the likelihood function is going to be over mu and sigma x1 through xn, right? And to no surprise, this is going to look exactly like this. Yes, question? Yeah, hold that question for a moment. What we see is that this expression over here, in case of the Gaussian, what we thought of as the density function, also we can repurpose it as our likelihood function. The difference is that in case of when we think of this as a density function, right? The data is the function is defined over the data space, right? But when we define it as a likelihood function, product from I equals 1 to n, 1 over 2 pi to the d by 2, sigma to the half, exponent of half xi minus mu inverse xi minus. Right? It is basically the same expression, but we are interpreting it differently. We consider when we see this as a likelihood function, we think of the parameters to be the variables, right? And your data to be given, right? When we reinterpret this as the probability density function, we think of the data as the variables and your parameters to be fixed. Yes, question?
So if you write something like probability of mu comma sigma given
So the question is, when you write probability of mu comma sigma given x. So a small correction over there. When we use the term probability of data, right? We never use the term probability of your parameters, and we use the term likelihood of your parameters. Right? The correct phrase is to use is probability of the data given parameters and the likelihood of the parameters given data. Right? That is the only difference in terms of mathematically, but semantically we are treating the data as the variable here, but the parameters as variable here. Other than that, the expression is just the same. And another obvious way in which they are different is if you integrate your probability density over its variables, you get 1. Right? But if you integrate your likelihood with respect to for your parameter space, it may not even exist. Yes, question.
Would it be right to say that likelihood forms one particular slice in the distribution curve?
Does the likelihood form one particular slice in the?
Represent one slice.
That's a good question. So let's kind of go over that again. So assume this is your probability density function, right? Now the shape of this curve and the position and everything about this curve is kind of fixed by the mu and sigma, right? And the x-axis is data or observation. Right? Now the likelihood for this is going to be mu sigma, and this is likelihood, and here it was the probability density. And the likelihood function is going to take some shape, and your training data is going to decide what the shape of this is. Right? So that's you got to think of it this way, where the this would probably again be some kind of a upward bending, but the x-axis over here is data, the x-axis over here is mu and sigma. So this is probability and this is likelihood. So if you are given a different collection of training data, your likelihood function is going to take a different shape, be located somewhere else. It may take a it may look very different, and this may not even integrate over to 1. The area under this or the volume under this under the likelihood function. But for a probability density function, the parameters will decide the shape, and the volume under this function will always integrate to 1. So it's the analogy of taking a slice. It doesn't quite hold. They're just two different. You think of them as two different functions. Yeah.
So is the correct interpretation the graph so given all the data from x1 to x and all those vectors, what is the best mu or sigma based on that?
Exactly. So the problem that we're going to attack with the likelihood function is, given the training data that we have, we want to choose some mu and sigma that maximizes the likelihood the most, right? And that's basically like the big picture of what we do in statistics. You're given a data, that data is going to implicitly define some kind of a likelihood function, and now we want to find the parameters that make the given data most probable.
And like this maximum is guaranteed. Like there will be a maximum.
I'm not intentionally not going to go into the details of, will a maximum always exist or not. But this is the intuition you want to have. There are technical conditions that make a maximum exist and things like that, but that's beyond the scope. For most of our problems, this is the intuition that you want to have. The likelihood is a function defined over the parameter space, and the shape of the function is going to be different according to the data that we have, and the probability, which is like the other way, it's defined over the observations or the data, and different parameters is going to give you, different probability density functions. There was another question? Yes.
I was just wondering, so in machine learning process, so you would go over the likelihood one first, and then you would create a model to predict future data.
Again, hold that thought. We're going to talk about what how we're going to extend this into machine learning. But this is classical statistics. What's likelihood? What's probability? Right? Yes. Question.
When you get a return like UN sigma, then you can exactly find the probability distribute the function.
Yes. So the question was, when we, based on based on the training data that we are given, we can estimate a mu and sigma, and that mu and sigma is going to define some probability distribution, and using this distribution is what we're going to use for making predictions over future data. That's the rough idea, right? So that's maximum likelihood, and the procedure that we're going to follow is in some kind of an abstract in an abstract way. If L theta given x is the likelihood function, take some form where x is so suppose we are given some training data, and we make an assumption that it belongs to some distribution, for example, the Gaussian, right? The likelihood is going to take some form, and that's going to be of the form of some product of I equals 1 to n, L of theta of xi. I'm intentionally not expanding out what L is. It could be a Gaussian like that. And the maximum likelihood procedure basically tells us that theta hat. So in general, we use the notation that we're going to use is we're going to put a hat over things that are estimated, right? Things that are given to us, like training data, are we just use them as variables. But things that we estimate as the output of some estimation process, we're going to put a hat over it, right? And theta hat, and I'm going to use the subscript MLE to say that we use the maximum likelihood procedure to estimate this, is going to be arg max of theta of I equals 1 to n, the likelihood of theta for each xi. Right? So think of, for example, in case of the Gaussian, you can think of this expression coming in over here. Right? And further, I'm going to make this claim, and this is always going to be the same as argmax of log of product of I equals 1 to n L theta. What did I do here? There was this function, the likelihood function, defined over all your training examples, and I make a claim here that instead of maximizing this, the product of these, I'm going to maximize the log of the product of these. Okay? And why is this true? Log is a monotonically increasing function, and if we want to, the theta that we obtain with this will always be the theta will always be the same as the theta that we obtain with this, right? Because it's a monotonically increasing function. Yes, question.
Instead of trying to find just like the parameters given the data, we can practice. Can you also try to maximize the likelihood over like a couple different distributions? Because like just given x vectors, we don't really.
Okay, let's keep that question for I'm going to answer that after that. Just because I'm running short of time, I want to cover a few more things. But in general, we're going to assume some form, some probability density, and just going to work with that. Right? Now, here the we replace the thing that we want to maximize with the log of the same thing. It's important to note that here we are calculating the argmax. If we were just calculating the max, then of course these two are different. But here we are calculating the argmax. So the theta that maximizes this will also be the same theta that maximizes the log of this, right? Because we're doing the argmax. And this can now be written as argmax of theta, sum of I equals 1 to n, small l of theta xi, where L of theta is equal to log of the right. So the log of a product of a few terms is the sum of the log of the individual terms, right? And and we replace the function L with the log of itself. Okay. Now, what would happen if L were to be a Gaussian? If we assume that our training data X is coming from a multivariate Gaussian, we would then plug in. So far it's a standard template. No matter what problem that we have, this is the recipe that we're going to follow for maximum likelihood estimation. And to take this further, we now have to get into the functional form of what the likelihood function actually is for that problem. Right? And in this case, for Gaussian, it's going to be argmax of. Now, so far we were just talking about theta in general, but now we're going to talk about the parameters of the Gaussian. Here we were, by theta, we were just mentioning the parameters of whatever distribution that we're going to use in an abstract way. And sum over I equals 1 to n log of this whole thing, 1 over 2 pi to the d by 2. This is going to look a little big, but it's going to simplify, I promise. 2 exponent of minus half x minus mu transpose sigma inverse x minus mu. Right? So, can we simplify this further? Yes, we can. So there is an exponent and there's a log, right? So the exponent and log cancel out. And it's the log of the product of two terms, and that can be broken down into the sum of the logs of the individual terms, right? And here I'm going to use this as mu hat, comma, sigma hat. And this is our max mu, sigma, and sum over I equals 1 to n. So I'm going to break this down into three parts. Right, 1 over 2 pi to the d by 2 and the log of that. It's going to be some constant. It is some constant. There are no variables there. So I'm just going to write that as some constant k, right? Plus log or half log of the determinant of sigma, right? Is it plus half or minus half? Sorry, minus half. Plus log of the exponent, they're going to cancel, and there's a minus half x minus mu transpose sigma inverse x minus mu. Right? And now, this is some function. This whole thing is some function of mu and sigma. We're going to think of x as given. This should be xi. Now, how do we do the argmax? Calculus, right? Take the derivative, set the derivative equal to 0, and solve for mu and sigma. Right? And we have time to do this today? Yeah, we have some time. So here, and this is where the things we reviewed over the last couple of days are going to come in handy. We saw how to take the derivative of quadratic forms. We saw how to take the derivative of a log of a determinant of a matrix. Right? And those things are going to be used right away over here. What was the question again? So this is the summation applies for the whole thing. The summation is for all the terms in there. So I'm going to write it out here. So we need to maximize this with respect to two variables, mu and sigma, jointly. So we're going to take partial derivatives. So let's solve it separately. So this is for mu and this is for sigma, right? And so the derivative with respect to mu of the summation I equals 1 to n k times minus half log sigma minus half xi minus mu transpose sigma inverse xi minus mu, right? And when we take the derivative, and this is going to be sum over I equals 1 to n, derivative of k with respect to mu is 0, derivative of log determinant of this with respect to mu is 0, and all what we are left with is the derivative with respect to the quadratic form, right? And so we saw that the derivative of x with respect to x transpose ax is equal to 2ax if it is symmetric, and sigma is symmetric. It's a covariance matrix. So covariance matrices are always symmetric, right? And there is a half, and there's and the half is going to cancel with the 2, right? And this will give us minus xi minus mu So let me expand this out to in case it causes any confusion. We're going to expand this out, so that will give us so minus half is common for everything. Xi transpose sigma inverse xi. So this is just the distributive property of multiplication. You take every pair and write it out. Minus xi transpose sigma inverse mu and the other way minus mu transpose sigma inverse xi plus mu transpose sigma inverse mu. Is it clear how we went from this step to this step? It's just the the distributive property of multiplication. And now we still want to take with respect to mu, right? And this is equal to sum over I equals 1 to n minus half. Right? This has no mu in it, so this is just going to be 0. This and this are the same thing because it's a scalar, and you can take the transpose of each other. Right? So I'm going to write this as, let me still retain to mu. This is going to be sigma inverse, and the transpose of that is the same, xi transpose mu minus 2 of that plus mu transpose sigma inverse mu. Right. And now take the derivative in, it's going to be I equals 1 to n minus half, and the 2 cancel out, and this will be with respect to mu, so this is just sigma inverse xi, and this is the quadratic form, and that's going to come with a 2, the 2 and the 2 cancel, this is going to be a minus 2, the 2 cancels, sorry, sigma inverse mu, right? And then we set it equal to 0 and solve for mu, and this will basically give us that n times, because it's a summation over n times sigma inverse mu equals summation I equals 1 to n sigma inverse xi, and sigma inverse you can take it out, and I'm going to continue it here, and that will give us basically sigma inverse mu is equal to sigma inverse 1 over n I equals 1 to n xi, right? And multiply with sigma on both sides, you get mu equals 1 over n I equals 1 to n xi. Right? So mu is just the average of the x's that are given to us. It looks pretty tedious. It's something you want to go back home and rederive it on your own just to make sure you're comfortable with it. And this is going to be probably the last time we're going to do such detailed derivations on board, right? Going forward, I'm just going to defer it to you to verify the derivations, but this is the essence. Now, what about sigma? We want to estimate the parameter sigma, but we see here that we have a sigma inverse, right? How do you take, that makes it a little complex, right? So, what was the question? Well, so sigma inverse is not the same as 1 by sigma, because sigma is a matrix, right? What is 1 over a matrix? There's no such thing as 1 over a matrix, right? You have a matrix inverse, which is another matrix, right? So now for doing it with respect to sigma, we're going to use a change of variable trick, which means we are going to consider a variable s, which is equal to sigma inverse, and make the observation that the gradient of some function L with respect to s is equal to 0 if and only if gradient of respect to sigma inverse of L equals 0. Does it make sense? Right? And then we're going to solve it for solve for s, and once we get the s, we're going to invert it, and the inverse of that is going to be the sigma that we want. right? This is a pretty standard classical change of variable trick that you do with calculus, right? So this thing over here, so now we're going to take the derivative with respect to s, I equals 1 to n, half log, there's a minus, and so this will make it with respect to s, and minus half x minus mu transpose s x minus mu. It's going to be xi, right? And the derivative of a log determinant with respect to the matrix is S inverse. It's not 1 by s, 1 over s, it is S inverse. And we're going to sum over n such things. So that is going to be n times S inverse. And there's a half outside. So, minus, what's the with respect to A of x transpose AX. So we saw what it is with respect to x. What is it with respect to A? I'm going to leave it as an exercise, and you will have to verify that this is just x transpose. Right? Yes, question? So I took a half s outside. Is there another negative? There's probably another negative. Oh yeah, so that's where the negative comes in. So the log, so log of 1 over something becomes the negative of the log of something. Right, so that's where the negative got cancelled out. I'm sorry? I mean, there's one, but this should be, yeah, that makes sense, sorry. And minus sum I equals 1 to n xi minus mu xi minus mu transpose, which means s, and you set this equal to 0, the half cancels, and you get s inverse equals 1 over n I equals 1 to n xi minus mu xi minus mu transpose, right? And S inverse is equal to sigma, right? So sigma is 1 over n xi minus mu transpose, and this, you know, it's similar to expectation of x minus expectation of x square, right? You can kind of see the similar, exactly, right? And that's your covariance matrix. This question? There was a minus that absorbed the 1 over s as determined. Yeah, right. So anyway, so if you have questions about this, you know, come up to stage after the lecture. But this is you know, this gives you a flavor of how to do maximum likelihood estimation, right? And you know, you're expected to be comfortable to do this kind of matrix calculus to derive maximum likelihood estimates, right? And we're going to be doing a whole lot of such matrix calculus, you know, throughout the course for different kinds of models. And this is just a simple model, a multivariate Gaussian, where you know, where this gets used. Now, what are we going to be doing for linear regression? I don't think we have time for linear regression, but maybe, you know, just give you a flavor of what linear regression is about. So for linear regression, it's a supervised learning problem, and a supervised learning problem is a problem in which we want to learn relations between x and y. So we're going to be given training sets in the form of xi, yi pairs, right? You're going to be given pairs of xi, yi, where xi is some kind of a vector, a d-dimensional vector, and we are going to be given n such pairs, right? So this terminology means it's a pair of xi and yi, and you have I from 1 to n, you have n such pairs, right? That's the terminology we use over here. And y is going to be in R, and we want to learn a function, right? We're going to call that function as h of x, and we want h of x to output y, right? And this h is going to be parameterized by some theta, and in this case theta was mu and sigma. Over here theta is going to be something else that we're going to see. And from the given training data set, we want to learn the function h theta of x, which means you're given a training set, right? From this training set, you're going to construct h theta. So this is called the learning process, the learning algorithm, right? This was xy pairs, and the output of the learning process is an algorithm, right? So the h theta is the output of the learning algorithm itself, and into h theta we're going to feed new x, let's call it x star, unseen x's, and it's supposed to output y's for the unseen x's, right? This is like the macro setting of regression problems or supervised learning problems, right? And in the next lecture we're going to see a couple of algorithms for learning linear relationships between x and y, and that's going to be linear regression.